So, my name is David Medliner. Thank you for the introduction. Some of you may have heard me yesterday. Who has heard me yesterday? Hands up. Okay. Don't be bored. There will be some repetitions. Okay, so today we are talking about solid rocket engines, the design, implementation, and we will talk about the benefits, advantages, and features of these engines. So there will be a short introduction to the technology. Then we will give some propulsion basics, so basic physics, thermodynamics, and then I'll talk about a design we performed. And later in the week we will talk more intensively on the design. So this will only be a short introduction to this design. So, solid rocket engines. There are different applications. So, they can be used as strap-on boosters for launch, as everybody knows from the space shuttle, but there are a lot of rockets using it, the Ariane, Delta, and so on. They may be used as upper stage for orbit insertion. Sometimes they're used to spin and de-spin space vehicles, sometimes before orbit insertion, so the burn is more stable. They are of course used for strategic and tactical missiles, so the military is very interested in them. And sometimes you use them as gas generators for start and pressurization, sometimes even as a fire extinguisher. And very important, if something goes wrong, you have to react quickly. Then it's the best way, if you want to abort a mission, to get the crew to safety. So, this is a principal diagram of a solid rocket engine. So, in the further part there would be the payload, so it would be much longer normally. And the motor itself is composed of the fuel, the grain. This is a solid part, that's why it's called solid engine. And we have normally an ignition charge at the head, but this is not necessary. Sometimes you see fuses that are inserted from the nozzle below, so the motor is ignited from the lower part. And then we have the working horse of the assembly. That's the nozzle, and of course the seal. Without a seal, the rocket motor wouldn't work properly. It was just stream out gas from every direction, and if that happens, it can have catastrophic consequences, as we know. Everybody knows the Challenger rocket. Oh yes, this is, I will present that later. Thank you. Hiya. So this is the solid rocket engine. So this is mainly the same thing. So we have here in front the seal, then inside, there are no grains inside, it's not loaded, nobody has to panic. It's totally secure, and then the nozzle afterwards. Okay, so that's why solid rocket engines are so favored still, because it's so simple. Of course, we can do a lot of chemistry, and you can improve on materials and so on, but the principle schematic is always the same. So what are the pros? So the benefits. It says very high thrust, so you can achieve so much thrust that you can lift off a very, very heavy rocket. It's a problem, like for a space shuttle, or for any other big rocket at the moment. They can't not lift without their boosters. So it has simple design, as you've seen, and it's heritage. So there are so many designs around that you can just look at them, copy them, improve them. You have not to worry about new things. Their ISP, the so-called specific impulse, this is a number that measures the performance of the engine, is moderate. So it's a medium ISP between the worst at 120 that are seriously used and to 300 seconds in the high-end military applications. There's normally a good mass ratio, although this is very complicated to get it, so you need to use compounds with carbon fiber and fiberglass and so on to achieve a good mass ratio. So this one, for example, has not a good mass ratio, because this is made of steel completely. And very important for some folks, immediately ready for operation. So you have it here, you take it, you shoot it. It's very fast. Nothing with liquids or something like that you have to pump in or pump out or something, just shoot it. So that's the pros, now the so-called benefits, and now the features. Not inherently safe. Sometimes they do things that are not in the rule book. So always keep a distance when you use solid rocket engines. They are not inherently safe. They can explode at any moment without notice if they are loaded. You need quality assurance. So you cannot build a solid rocket engine and just shoot it. Okay, just build it, assemble it, and shoot. You have to really be very proper in your instructions how to assemble it. You have to be careful about the grains. When you produce it, you have to produce it the right way. You have to look at it maybe with X-rays or ultrasound or any other way possible. They are prone to mishandling, so don't play with them. Don't go near it with lights. Don't let them fall. Okay, that's all things that could, mishappening happens. And they're very difficult to throttle and shut down. There is technology to do that, but it's not straightforward. Normally, if you ignite a solid rocket motor, it just burns out. You cannot stop it. It's an unstoppable force. So you have always reckoned with this problem that once a solid rocket engine starts, there's no going back. This was one of the great design flaws of the space shuttle. Once the space shuttle, the boosters had ignited, there was no going back, no way to save the crew. And from an environmental point, very important, often they produce toxic exhaust and have toxic propellants. Not all of them, but some of them use a lot of chlorine and fluorine and such ugly substances. Okay, so let's get to the igniter. So the igniter is normally electrically triggered. Nobody today uses a fuse with matches, okay? It's logical. But you need a safety protocol. You cannot just install an igniter and think that your computer will do fine, okay? You have to have some switches to shortcut the igniter, and you have to open them manually, not by computer, okay? And this have to be followed by a protocol. That is, there are some operators and some observers, and they will say, okay, everything is fine, area is clear, you can now take the switch off and arm the rocket and so on. So you have to be very aware when you insert the igniter at the last possible moment. So from this point on, the rocket is really dangerous. Okay, and the igniter, of course, generates a lot of heat and gas because it has to start the engine and uses normally a very exothermic reaction. It can be used, for example, thermite, or what's very nice is Teflon with magnesium or something similar. Okay, so it's to the grains. The grains is essentially the fuel, but they are formed as cylinders. And it is an intimately mixed mixture of oxidizer and fuel, so something burns something else. Normally, there are cylindric sections of the solid propellant, and these are called grains. And you can add a special binder to it, like rubber, to increase the mechanical properties, because during flight, solid rocket engines have a very high thrust, so they can have a very high acceleration. There can be a lot of vibrations, and the grains are very prone to cracking. If they crack, the whole thing goes boom. Okay, so they have to be very sturdy, the grains. So they burn over an exposed surface. So when you insert them into the engine, not all surfaces of the grain will burn up. It's just as it is designed. And the geometry of this exposed surface controls the evolution of the thrust of the engine. So you have to be very careful how you design the geometry of the grains. The burn rate itself is dependent on chamber pressure, and it's the key parameter for solid rocket engines. So they are designed to work at a certain pressure. Normally, one chooses something between 40 and 70 bar. The higher, the better, because at higher pressures, first, of course, the thrust is higher, the burning efficiency is higher, and there are no burning instability. So if the thrust, the pressure in the chamber goes too low, the motor can shut off, and then start again. So it starts to chuff. Okay, so it's good to be at a high pressure. The problem is the higher the pressure, the more heavy the container has to be, so it can withhold this pressure. And if the pressure goes too high, then of course it will deflagrate and burst. So, and very important, and it's used in a lot of solid rocket engines, you can add metals to the fuel. Also metal to the pedal, but in this case, you just insert magnesium or aluminum. It has a very high exothermic reaction with the oxidizer, and then increases the temperature to a point that it really matters. You can get 20–30% more thrust and specific impulse for the same amount of fuel. So Let's talk about grain geometries. I told you there's cylinders and there is a burning surface. And in the burning surface, the form of the burning surface is very specific. So you can use just a plain surface and you burn it from one end. That's what's normally used in pyrotechnics. Very simple, very straightforward, burns a long time, but produces very low thrust. Okay. So the second that we are using is baits, where you have a circular hole, and the cylinder burns from inside and from the adjacent side of the cylinders, but not from the outer side. And then there is the moon geometry, where you have an eccentric hole. So when it burns up, it forms like a moon, and this has the advantage that it has a very smooth thrust. The problem is that at the end, one side of the container is exposed to the hot gases, so you have to isolate it. Then there's a star geometry. It's used if you want a very high thrust at the beginning, at the start of launch, and then later on something less. And then there's a C-slot. It's very similar to moon. And rod and tube. And rod and tube is one totally neutral burning, so you have thrust, neutral thrust over the whole burning time. But this is difficult because, of course, the rod in the middle can break, and if something breaks, if a fuel part breaks apart, and of course it will go down in direction to the nozzle, and when the nozzle is reduced in diameter, so the throat is less open, then the pressure inside the chamber will rise up very fast, and then the regression, that is the burning rate, will rise up too, and then will produce more gas, and that can lead to a chamber burst. So this is a difficult design. Okay, so propellants. Black powder, everybody knows black powder. We'll talk about them in detail. Then zinc sulfur was used in the 60s up to the 90s. Nowadays, not, well, it's used by amateurs. Then candy, that's what we use. Right? You can eat it, but it won't taste very good. And double base, which is military standard since a long time. Today, mostly all used fuels are composite fuels. Then there are high energy composite fuels, and especially for the military, minimum signature fuels. So let's start with black powder. Everybody's seen it. It's made of charcoal, calcium nitrate, and sulfur. Very simple, and is known for thousands of years. It's very cheap, as I said, oldest pyrotechnic known. And the grains are made of pressed powder. So you take the ingredients, you grind them down, you press them into a grain, and the problem is, of course, this stuff is very sensitive to electrostatic discharge and so on. And all of you have heard about powder mills blowing up and so on. This is very dangerous stuff, so don't do it at home. Let professionals do it. Because the grains itself, because they are made of powder, they are sensible to cracking, of course, because the adhesion between the grains are very high. There's no binder in them, so they cannot hold just by the adhesion by the pressing. It is very poor performance, about 80 seconds, but it's enough to lift off the pyrotechnics. And it's only used, as I said, in pyrotechnics in very small amateur rocket motors, so for beginners, for example. So then there's zinc sulfur, very exothermic reaction. The problem is only that it does produce a solid, so not so much gas. And this, of course, leads to reduction in thrust, but it is very impressive. So a lot of smoke, orange fireball. So just zinc and sulfur, again, very cheap. Grains, like with black powder, made of pressed powder, a little bit more stable. It has a very fast burn rate, so you can achieve burn rates up to 2 meters per second, so a normal grain of this size is just gone in some milliseconds. It's very fast. It's very poor performance, worse than black powder, about 60 seconds, but it has very impressive smoke. So it's only used for pyrotechnics and amateur rocketry. Then we have candy. That's our preferred propellant at the moment. And candy is made of a nitrate oxidizer. We use sodium nitrate and some polyalcohol, or known as sugar. So you just take one sugar. There are different sugar, fructose, glucose. We use sorbitol. And what you essentially do, you mix them in a melt. So it's very cheap and non-toxic. You can eat every ingredient, of course not in too much quantities. Yeah? It's sugar, it's nitrate, that is essentially a salt that you can eat. We add aluminum powder. Okay, aluminum powder is not very tasty, but it's not really toxic if you not inhale it. And we use rust as a catalyst. So the grains are made from cooled melt. You melt the sugar, you add the oxidizer, you turn it around, you put in the ingredients, and then you let it cool, and that's all. But of course, you have to be very thorough with your temperature curve. So you have to do it at, in our case, at about between 130 and 140 degrees Celsius. And you have to make it very smoothly, you have to turn it around, and after a time, you just cool it slowly down. So it needs some hours to cool down and some days to be usable. So it's mechanically brittle. Of course, everybody knows candy is brittle. Right? It's not very soft. Toffee is soft. We could make toffee, but it doesn't work at the moment. And the salt element is brittle too, so it's very prone to cracks. So one cannot build very large grains from them. If you look at this motor, it has a diameter of 12 centimeters. That's almost the maximum possible at the moment. So we could go to, let's say, 16 centimeters, but then it's really dangerous. Because when you have a crack, then it blows all up in one quarter of a second. So it has a fair performance. The standard candy without aluminum, about 130 seconds. And when you add aluminum, for example, you can go up to 180 seconds. So at the moment, this motor here has about 175 seconds, so we reduce a little bit the chamber pressure to be on the safe side. Okay, and it's used in the laboratory. The military has absolutely no interest in this because it's so mechanically brittle. It is not favorable for their applications. So the military normally use double base. It was first used for guns, for example here, the battleship Iowa. And it is made of two monopropellants, normally one very energetic propellant like nitroglycerine, and a second propellant like lactocellulose that works as a plasticizer. So one very aggressive substance mixed with one less aggressive substance gives some stable propellant. It has very little exhaust because it burns very clean. It has good performance, so some 100 seconds more than candy. And if you add aluminum or magnesium, you can get over 250 seconds, so it's okay. The problem is if you add metals, then you can again see the smoke. That's why you see, I think they have aluminum inside, because they don't care about being seen. So, and it's mainly used for military applications, but there are some amateurs using double base too, but it's difficult to produce. So, the normal rocket engine you see today is made of composite propellants, like for example the space shuttle boosters. They use a very strong oxidizer with a metallic fuel and an organic binder. So essentially, all of them are made with ammonium nitrate or ammonium perchlorate. And as you may know, ammonium perchlorate is very dangerous and is very toxic. So one colleague of ours, he has a degree in chemistry, but I don't know, 20 years ago or so, he blew off one of his fingers with ammonium perchlorate, a very small sample, and since then he can't hear on the right ear. So it's very dangerous stuff. Don't play with it around. Ammonium nitrate is difficult, but not that dangerous. So the binder you add provides a mechanical support because the oxidizer and the metal, of course, are powders and they wouldn't mix, and you don't want to press them. It's a very bad idea to press something like that, okay? It's too dangerous. So you add a binder, essentially all are made with hydroxyterminated polybutadiene, rubber, essentially, good burning rubber. And you mix them, and you can mix them at room temperature, so there's no problem with thermal curves and cooling and cracking and so on. But you have to be very thorough at production to not introduce bubbles, because every bubble is like a crack, an increase in surface when the burning front goes through. So in this moment you produce locally more gas, the pressure rises, and you produce more gas, and it is of course a deadly cycle. So it has high performance, normally about 300 seconds, and it's used for all applications. So the military uses it, the civil engineers use it, amateurs use it, and you can buy it. Okay, and then there are further developed composite propellants. These are called high-energy composite propellants, where you add to the mix some substances you normally wouldn't expect to find in a rocket engine. So it's basically identical to composite propellants, but you add like RDX or HMX, so substances you normally don't get. Yeah? They put very, very fine crystals in it, and there are even more aggressive substances than these two, and there are not a lot of substances that are so aggressive. And you can push up the performance and the burn rate to over 300 seconds. It's of course only used for military applications, and it's dangerous. So, and a few years ago, they found a new substance called hexanitrohexaazaisovulcetane, and it's a cubane, and it was found in China Lake. The guys that do all the ordnance for the Navy. And this is a very interesting substance because it had 20% more energy than RDX or HMX. It's nearly invisible when it burns, so it burns very good. And it's shock insensitive. It was very strange. It has only a hazardous class of 1.3, like our candy, so you can go with a hammer at it and no danger. It's very expensive, that's a problem, and you won't get it from China Lake. And it's only used for military applications. I'm sure the Russians have something similar. So, but that's nothing for amateurs, okay? So let's talk now about some physics, some propulsion basics. So we have done now the applications, and you understand now that there are different ways to do it, but there are some common things. First, most of us know, there's something we call linear momentum, and if you're an inertial observer and look at a system where no forces are interacting, then this momentum has to be constant. So if we look at the rocket in flight, and it moves with a certain velocity v, in the desired direction hopefully, then in the next moment, this is after some small time interval delta t, okay, so then there will be separation, ejection of mass in the opposite direction, so our rocket can propel forward. So, and of course, if it's a closed system, so the linear momentum must be constant, and then we get to this equation. So on the left side, we have the momentum before and after the separation of the little slab of mass. And then you can reduce it by just omitting all the terms that are double, and you divide it by the time necessary, delta t, and you get to an equation that you can integrate from one starting time to one end time. So t0 is the start of the burn, and t1 is the end of the burn. On the right side, we just integrate the derivative of the velocity, so we get the difference in velocity on the right side. It's something more difficult, and this is just a logarithm of the mass ratios. So we arrive at the celebrated Tsiolkovsky formula. This is the basic formula for all rocketry. Yeah, it doesn't matter how complicated or simple a rocket system is, it always has to obey this simple equation. And it states that the change in velocity the rocket acquires during a burn is proportional to the velocity, the effective exhaust velocity, I call it here u, and proportional to the logarithm of the mass ratio. So m0 is the mass before the burn, and m1 is the mass after the burn. So from this equation one gets, first, one should eject mass as fast as possible out of the rocket, so the rocket gets fast. And second, one should get a mass ratio as high as possible. That is, make the rocket mainly out of propellant and everything is fine. So the problem is that mass ratios above of exactly, I don't know, 10 or so are nearly impossible to make because, for example, for our rocket motor, you need something to hold the propellant during burning. Yeah, if it has 70 bars, I cannot take alufoil with 0.1 millimeters. It will not work. So in this case, this is steel casing with, I think it's 1 millimeter, 1.5 millimeters or so, and it can withstand barely the 70 bars. So when it burns, it really rises in size. Yeah, after the burn, you can see that it is a little bit bigger every time than before. So you always have to look at the engineering principles involved in the building of your engine and rocket and so on to achieve the highest mass ratio possible. So just to give you a perspective what is needed, if we want to go, for example, to low Earth orbit from Earth, there's always a main problem in going to space. First, you have to leave Earth. Without that, no space. So we have at least 9 point something to leave Earth, maybe 10. You don't need that much velocity in orbit. The low Earth orbit is about 7.3 kilometers per second, but you need the energy to get up, to go through the air resistance has to be overcome, and that's why you arrive at between 9 and 10 kilometers per second. So if you are in Earth orbit, then you can go anywhere, except maybe the sun, with very little additional power. So, for example, to go to a geo-transfer orbit, what most satellites do before going into geo, you need 2.5 kilometers per second. And from there to an orbit around the moon, 1.6. So it's 4.9 kilometers per second. This is not even half of that to leave the Earth. So once you're on low Earth orbit, you have all the time in the world, if you have the propellants and a small engine, to go to the moon, if you achieve 4.1 or something like 4 kilometers per second. Then to go down to the moon, you need again 1.6 kilometers per second. And to take off, because there's no atmosphere, again 1.6 kilometers per second. And if you look what you have to do to reach Mars, you see that it's much easier to go from the moon to Mars than from Earth to Mars. So the logical point of view to go to Mars is first to go to the moon, build a base, build there a big ship, or in lunar orbit, and then go to Mars, because you don't need so much delta V. So the problem is that normal rockets have an exhaust velocity only in the order of 1 to 4 kilometers per second. So how do you achieve 10 kilometers per second or more? Well, this rocket, for example, has an exhaust velocity of 1.7 kilometers per second. And it would never be able to achieve higher velocities. If we have a mass ratio of about 3, then you get an ln of approximately 1. And you would achieve exactly 1.7 kilometers per second. But again, there's air, so you normally get to maybe 1 kilometer per second. Okay? So if you want to go faster than that, you have to use staging. And the idea is just that you put several rockets on top of each other. Of course, one smaller than the other, otherwise the lower stages couldn't lift the upper stages. That's logical. And then you add your delta V's of these stages. And of course, you will choose the exhaust velocities of these technologies on the rockets so that you maximize the delta V. Normally, you use a higher U2 than a higher and the U1. So the lower stages are normally have a lesser exhaust velocity, but they normally have to only to produce a thrust to take off. So in the end, you get a mass ratio of the total rocket. So for example, if you look at the Saturn V rocket, you lift it off with about 3,000 tons, okay, and you land it on the moon with 30 tons or so. So you have a mass ratio of about 100, okay? And then of course, this ln factor gets larger. Okay, now something to thermodynamics. It's necessary if one talks about rocket engines with internal combustion, one has to know some simple things about thermodynamics. So it's the first law, sometimes called you cannot win. And this is the second law, you shouldn't even try. Okay? The first law just states there's something called the inner energy, U, and you can only change it by adding heat or adding work or getting something out of it. And the second law defines something that's called entropy. Okay, and energy and temperature are connected by a constant called the Boltzmann constant. Some of you may have heard of it. And these Boltzmann constant couples the mean energy per so-called degree of freedom, DOF, of any molecule and atom that is around us. So if you have a sample of air, for example here, at, what do we have here, 18 degrees or so, then you could put in T, of course, as an absolute temperature, 273 plus 18, multiply it with Kb divided by 2, and then you have the mean energy in Joule that one molecule of air has in a certain direction, so flying, let's say, in the x direction or y direction or z direction, or rotating. So this is the mean energy per degree of freedom. And then we have something that's called the heat capacity. Heat capacity is when you take a system and you put something energy in it in form of heat, then it increases, hopefully, in temperature. And how many joules you need for 1 Kelvin, that's called the heat capacity. So, and if this happens at constant volume, then you name it the heat capacity CV at constant volume. And there's so-called enthalpy that's useful for the heat capacity at constant pressure. So why did I tell you this? Because we need this number, the so-called adiabatic index. And it's very important for all rocket formulas because Every rocket formula has this adiabatic index. You don't really need to understand what it does. It's just a number. It's a number between 1 and 1.66666 and so on. So, there are another numbers I want to explain before showing you the formulas. There's Avogadro's number. Just the chemist's way to say a dozen. It's just slightly larger. And then it's the so-called universal gas constant, which is just the multiplication of the Avogadro number with Boltzmann constant. And because both of them are to the power of 23, just the one with a negative sign, they nearly annihilate to unity, so it's about 8 point something. Yeah, keep that in mind. So the amount of substance is just saying I have so and so much molecules, but the number is too big to write, so I say I have just one mole or so, or 2.5 or something. Is when you use dozens. You don't say, I would like to have 24 eggs. No? Please give me two dozens. So then it's a molecular weight, a very important number for us. It's just taking the weight of a single molecule and multiplying it with Avogadro's number, so you get the weight of molecules, of Avogadro numbers molecules, okay? So for example, for a certain compound like 12 carbon, it weighs exactly 12 grams. So you know if you have 12 gram carbon in your hand, it's exactly this number, 6.022 to the power of 10 to the power of 23 atoms. So this is a molar concentration. This is just how many moles per liter. Then the number concentration, how many molecules per liter. Mass density, how many kilograms per liter. And the specific heat capacity, how many heat capacity per mass. So, then there's something important for rocketry, is the sound velocity. We always want to break the barrier of sound. So how do you calculate it? Very simple. You just take the temperature of the gas you want to know the relative sound. You divide it by its molar mass, m, and multiply it with the gas constant, 8 point something, and then the adiabatic index. So if you look at the numbers that air has, then you achieve a velocity of about 340 meters per second at room temperature. So, and then of course very important, the Mach number. It's just how fast you go in relation to the velocity of sound. So let's talk about ideal gas. This is an equation that shows you what the pressure is that a gas exerts on a certain volume. And I found it very useful to imagine a bunch of hooligans confined to space V. So this is the space V, and N is the number of hooligans, and you agitate them, and this is a temperature T, okay? So on P is then the pressure they will exert on the environment. You can just put V on the other side, then you have the concentration of hooligans, and this is just the mole number. This is for the chemists, and this is what the chemists like too, with the concentration, and this is the form that you always see in rocketry. No? So all of these equations always describe the ideal gas, the pressure of the ideal gas. Yeah, and you have only to keep one thing in mind. The pressure is proportional to temperature. This is the higher the temperature in the rocket chamber is, the higher the pressure, the higher the thrust, and the lower the molar mass. That is, the smaller the things that come out of the chamber, the better, yeah, the higher the pressure. So what are the properties of ideal gas? The adiabatic index is very simple to explain. It's just the number of degrees of freedom plus 2 divided by the number of degrees of freedom. So if you have, for example, air, a molecule of air is normally nitrogen or oxygen. It's a diatomic molecule. It has 5 degrees of freedom. So 5 plus 2 is 7, divided by 5, 1.4. So for air, gamma is 1.4. Not exactly because of the ideal gas, but it's very close. So the difference in the both specific heats is just exactly 8.314, our universal gas constant. And you can directly calculate Cp, and this is important for the flow in the nozzle. So let's talk about the flow in the nozzle, gas expansion. First, we have to do some assumption. First, we don't look at two-dimensional or three-dimensional flow. It's too complicated, just one dimension. It's steady flow, so no time variations allowed, adiabatic, no friction, no chemical reactions during the flow, ideal gas. We do only volume work. The gas just expands. It does not do anything else. And the rocket motor is not very large, so there will be no significant length to fall, so no significant change in potential energy. So this is the normal view of a flow, in this case around an airfoil. And if you do these assumptions, there is a constant of the flow, and it's called the stagnation enthalpy. Yes, and this stagnation enthalpy is just the inner energy plus PV divided by the mass. And it changes when it's flowing, it lowers, the enthalpy lowers of the flow. And if it stagnates at one point, for example, this red point here, this is a point where the air does not move. So there's no relative movement between the foil and the air. And a very similar case, for example, for a rocket, when it flows through air, then the tip of the rocket, there is air on top of the tip of the rocket that does not move, okay? So at this point, the flow achieves the stagnation enthalpy. And this is very important because this is directly connected to the temperature by this relation. So if you know the specific heat by constant pressure, you just can calculate the enthalpy by multiplying it with the absolute temperature. And as you have seen, for ideal gas, we can calculate that. So you can calculate from this equation by dividing by Cp the temperature of the tip when you go through air at a certain velocity v. Okay? And you can see by calculation that at velocities larger than about Mach 2.53, the temperature gets so high that you really have to think about how to build the tip, otherwise it will just melt away. Yeah? So reaching temperatures of about 500 degrees. You cannot take aluminum, it's not possible. So back to the nozzle. In 1888, the engineer de Laval developed this very simple device. This very simple device is now so-called de Laval nozzle, convergent, divergent. It looks very simple, nothing complicated to it. But this simple device produces more power in the world than anything else. Every steam engine works with a Laval nozzle. So every time you switch on anything, somewhere a Laval nozzle is doing the work, okay? So every normal power plant is using Laval nozzles. And of course, in rocket engines, we use it too. And rocket engines, as you may know, are the most powerful engines ever built. So it's a very simple device, no movement. Why is it so powerful? Because it's non-cyclical. So it has a very, very high efficiency. And what happens is that very hot gas comes from the burning chamber, goes into the converging region, accelerates, and then at this point, at the throat, reaches exactly Mach 1. But Mach 1 for the local temperature. And as the temperature is very high, Mach 1 can be 1 kilometer per second or more. And when it leaves this throat, it even accelerates more. So it can achieve multiples of Mach. And you can get exhaust velocities up to 4.5 kilometers per second with a simple chemical device, or even 10 kilometers per second with a nuclear engine. So, back to thrust. Okay. We have, during the reaction, a certain chamber pressure, and this pressure is exerted on the surroundings of the chamber, and hopefully the chamber doesn't crack. So the gas cannot flow out. The only way to flow out is through the nozzle. And of course, that's what we want. And at this point, the pressure is not zero, but has some exit pressure, we call it. And as we start here on Earth, we have some ambient pressure. So the total thrust the rocket produces is made up of two terms. The first, m point VE, is due to the impulse that the flowing out of mass exerts on the engine, exactly on the nozzle. And the second part is some pressure part that depends on the difference in pressure at exactly this point. And what it essentially does is that when the gas leaves the nozzle, it may even be propelled more by the pressure if PE is higher than PA, or it may be decelerated if PE is lower than PA. And the problem is if PE is too low, let's say 4 or so times lower than the ambient pressure, then there can be a separation of flow, and it will begin to move the flame, and this is very dangerous for the rocket. So you have to design the nozzle so that you don't have a too low exit pressure. So the effective exhaust velocity U for our Tsiolkovsky equation is just calculated by dividing the thrust by dot m, and that's what you get. The problem is how to calculate VE. Also, by the way, the specific impulse is just the thrust divided by the flow of mass in kilogram. So if you have the thrust in kilopond, you just divide it by the amount of mass that flows out, and you have the specific impulse. For example, if an engine produces 150 kilopond of thrust, and it flows out, let's say, 1 kilogram per second, then it has exactly 150 seconds specific impulse. So this is the equation I talked to you about. This calculates the velocity at the exit of the nozzle. And what we need is, of course, the adiabatic index, but you know this is a number between 1 and 1.66, depending on the combustion products. And we need the molar mass of the combustion products. We need the stagnation temperature, but it's not exactly the chamber temperature, but very close. Then we need the stagnation pressure, but it's nearly the chamber pressure, and we need the pressure at the exit of the nozzle. Okay, you don't know that, but you can say, okay, just take half of ambient pressure, so 0.5 bar. And if you look at the equation, you see that hidden in there, there is the velocity of sound, the velocity of sound in the burning chamber. So the velocity of sound in a burning chamber is proportional to the exit velocity of the gas. And if you put everything in, you can calculate the thrust by this equation. Okay, I won't go into every detail, but you know it's just numbers. Just set them in and you get the thrust. So let's talk about design. How do you design a rocket with a solid engine? First, you have to define mission requirements. This is very project management style, okay? NASA invented project management, so there will be some very similar points. So you define the requirements, and then before you proceed, you think about how do you evaluate my solution. So you have to think about evaluation criteria, and then search for mission alternatives. Are there different ways to do the same thing? And then you begin to define your vehicle and what technologies you want to use, or in our case now, let's say a solid rocket. And you design the propulsion system. And finally, you assess the feasibility. Is it doable? Can we do it in a certain time frame with certain money? And then you choose what's best and hopefully document it. And then if this doesn't work out, repeat until you're ready. So in the case of the rocket, well, it's only the motor of the rocket, the Arguna 4 we call it. We had some very clear mission requirements. We want to reach a peak altitude of at least 8 kilometers, maybe 10. We want to take with us at least 5 kilograms of payload. And we want to use telemetry during flight, so in case something goes wrong, we know what did go wrong. And we want our payload back. So this is not, you have to do it quite thoroughly, otherwise the design is terminated and there's no way to get your payload back because there are no parachutes, okay? So then we need some evaluation criteria. And this is, are we using something new? Then it's bad. No? The more new technologies you use in a certain project, the more dangerous it can be. And what are the prices of the components we need? So these were our evaluation criteria. Then we thought about mission alternatives. The problem is the launch is impossible in Absurdistan and Bureau, Croatia, also known as Germany. So we tried for years. It is impossible. You just don't get anywhere here. It's not possible today. Maybe someday. So we will launch either in Denmark, in Tranum, northern part of Denmark, or we launch in Poland, in Drawsko-Pomorskie, where they have a very large area that is normally for the military. Both areas are. So this is step 3. Then we had to think, of course, of the vehicle itself, and there are different parts. We will present them in another lecture. It's, of course, the nose is very important, the recovery system and the parachutes, the payload bay, the payload itself, avionics, then antennas. It's not so trivial to build antennas at a rocket flying at Mach 2. You know, everything falls off. Then a rocket motor, this one, based on Suka. Suka is our term. It's super candy, so it's supercharged candy. By adding aluminum, it gets really hot. And of course, the fins. Fins is something, oh, we're boring, fins. Well, without fins, the rocket would just fly like this, and if it loses the fins during flight, it will do the same. So don't lose your fins. There are so many rockets that lose their fins during takeoff. Very dangerous thing. So you have to put a little bit of effort into fins. Okay, so of course the propulsion system, but we have tested some. So we wanted to take a single solid rocket motor, no staging, because staging would require new technologies that we don't have at the time. We take a Laval nozzle made from graphite. Graphite is the best material ever. And then we take 9 Bates grains. Every one of them has about 2 kilograms of 2 point something grams, so we get to 18 kilograms in total of Suka propellant. So you have to imagine that normally, if it's fully loaded, the motor contains 9 cylinders about this length, and every one of them weighs 2 kilograms. And we wanted to achieve about 30 kilonewton seconds, so an O-class motor. From our simulations, we knew that we needed at least 30 kilonewton seconds to achieve 8 kilometers. So then you assess feasibility, that is you test the subsystems on smaller rockets. We have smaller rockets, so we took the avionics, flew it with a smaller rocket, tested the telemetry, the antennas, and so on. Of course, the large parachute not, would be too large. We did a lot of motor testing on ground, and of course, a lot of simulations. So, to give you just an example, this is a motor test we conducted 2.5 years ago, and it burns for about 3 seconds. Okay, this is just the exhaust getting out. This produces still a lot of thrust. To get your perspective, this is kilonewton. So 10 newton is 1 kilogram. So 10 kilonewton is 1 ton. This thing produces a thrust of 1 ton. So it could lift off a car, barely. And it burns for 3 seconds. And it makes a lot of sound. So I wanted to show you, wait a second. I'll show you just a video. Because seeing is believing. So this is a test conducted okay. This is the wrong one. Okay. So preparations. Start slowly. Okay, you cannot hear anything, but it's very loud. If you stay at 200 meters, you think that something is going on in your stomach. It's very impressive. So this was the first test we conducted 2 years ago. And this is from this year. From this year. New grains. So just to give you a perspective, this burned for about 1 second and produced 1 ton of thrust, okay? So once again, because it was so short. Okay, and if you put this on a rocket, it will go to at least 4 kilometers or so, yes? Just with 1 second of burn. And it goes away so fast, you can't follow it. It's just, okay, that was it. And we will see that later. We have another lecture where we'll show you videos of how the rocket progresses through the air. And this is one close-up look. So there was something wrong at the beginning. The burn-off didn't go so well. The igniter didn't work well. So you have bad burning at the beginning. The chamber pressure is not high enough. And now it takes off. Okay? So it's very important to design an igniter the way that it produces enough gas and heat to thoroughly ignite the motor before takeoff. Otherwise, it may take off slowly and fall off and then go on, and then you have a rocket that goes at 45 degrees somewhere. Okay? So designing an igniter is important too. So, for the moment, that's everything. I hope you enjoyed my talk. Any questions?
So we have 5 minutes left for the questions, so please come to the front if you have questions. Question.
Could you tell us more about the composition of the candy?
Everything before candy.
Can you tell us more about the composition of the
Yeah,
candy?
sure. The candy is made of, as I said, sorbitol. This is a C5 sugar. You can buy it in every supermarket as a sweetener. And we use sodium nitrate, which is when you can buy in Poland and Holland. In Germany, it's difficult. In Germany, you cannot do anything. Then we add some carbon. Carbon is to improve the ignition properties, so it can burn faster. And we use a little bit of iron rust, Fe2O3. So this has catalyzing capability, so we increase the burning rate. And we have, of course, on our website, there should be a link. We have a patent. Well, one guy that invented this thing, he made a patent, but we don't want to make any profit out of it, just so anybody can take it away. It's free for every amateur who want to use it. And if anybody wants to know the exact receipt, you can just contact us. Okay?
More question?
About candy. How much does it cost?
2.5 euro per kilogram. I've calculated it myself.
Is it really candy, like gummy bears and chocolate?
Well, let's say the sweetener would just will be like gummy bears or so. Yeah, it's just sweet. But sodium nitrate is used for, I don't know how to say it. It's a salt, Pökelsalz. For anybody knows what Pökelsalz is in English? No, guess so. So yes, this is need for meat. Yeah, so it smells salty. And rust, well, I don't know, rust is not very tasty, and aluminum is, no, strange. But it's not toxic, that's important. Every other, the important thing about this propellant is that you have a non-toxic propellant with 180 seconds of specific impulse, and every other propellant you can choose is somehow toxic, or dangerous, or both. Okay?
Any more questions left?
I have two questions from the IRC. The first one is from Sven G. He's asking, if I wanted such a rocket, how much would I have to pay for it?
Oh, this is a common question. So if you want to buy it from us, about between 5 to 10 kilo euro, depending on the hardware.
Okay, and the second question on IRC is it legally allowed to make spaceflight devices with Moon Plus range without any license?
Well, as long as no pyrotechnics are involved, you can do whatever you wish. The problem is when you go to launch and you want to use pyrotechnics. So to manufacture anything, you can do what you want. That's not a problem. The problem is if you go to a launch site and want to get a launch permit, then, for example, in Germany, it's very difficult if you're not military personnel or a member of industry that is working with the military. But in other sites in Europe, this is very, very easy to fly on military environment. So, for example, in Holland, in the Netherlands, in Poland, even in Sweden, in Norway, it's possible very easily, in Denmark. So, as long as you don't fly, you can do anything. But at the moment that you use pyrotechnics and want to fly, then you have to look for the launch permit.
Thank you.
So if there are no questions left, I will say thank you to the speaker. Great applause again, please.
Thank you.